Wonderful, so that should be fine now?
Are they happy online?
Yep, seems so.
Do I need a mic? Can people hear me?
No, the mic is over there.
I see, right. So shall I just get on?
There it is.
Okay. I can't work out the clicker had. I'm trying to click. Oh, you can click.
It's not working for you? It seems to be working now.
So I shouldn't press that button. Oh, there's a delay. Oh, okay. All right. Let's see what happens. So thanks for the invitation. Lovely to be here in person. And let me stress, I mean, I guess most of you know already, but I'm not a computer scientist and I'm not a mathematics educator. I'm just a research number theorist. I didn't press anything that time. Is that just what we're going to, is that just going to happen? Oh, I see, and that goes backwards. Right. Who knew nothing about this stuff 5 years ago? I'm not in control. I mean, I can just press a button. I just want to go forward.
Sorry.
I'll quite happily press. There you go. That'll do. Yeah, I can go with the buttons. So in 2017, my youngest child started going to big school. I've been doing a lot of childcare. My partner's a surgeon and is extremely busy. And my youngest child turned 12 and started going to big school. I didn't need to take them to school in the mornings and I didn't need to be home for relieve the babysitter in the evenings. So I had more, more time in my life. And I was also teaching coincidentally, I was also on the Introduction to Proof course. Which of course I love teaching. And so I thought I've got the time to try something new. And so, the question I came up with is, can I use a theorem? I'd seen students do very poorly in this course. And I'd seen them struggle. The kind of questions you get, like, what's the method? At school, everyone, this is people doing my course. This is the first term, first year undergraduates in the maths department, and they're asking me what the method is to solve questions about equivalence relations. So the method is that you understand the theory, and you kind of like create some mental model, and then figure out the problems yourselves. That's the method, which is not really the answer that some of them want to hear. So I wondered whether putting that kind of idea within some context of a formal system would actually make it easier to teach students about equivalence relations. So that was the basic, turns out very naive and stupid idea that I started with. And over this, I started in June 2017, trying to get an overview of the area. As someone that was a complete outsider, and this was extremely difficult to enter the area at that time because there was nothing written for mathematicians, and I didn't know what a type was. In some sense, still don't.
Sorry, Karen, can I slightly move you here so that the people can see your camera and we can see your slide?
Yeah, this is absolutely fine. Thanks. So I tried to get the hang of the area and got some kind of idea as to what was going on, but found very little that I could do in practice. I couldn't. Where are the basic questions in? Where are the basic questions in number theory or in whatever, or in group theory? Where's the proof that the order of the element divides the order of the group? Yeah, that's to me sounds like an extremely basic thing. The order of the element divides the order of the group. And what I hadn't realised at all, and what nobody was telling me, was that somehow actually this is an incredibly complicated and profound thing, because finiteness is an incredibly hairy concept. This was something I hadn't really realised. The concept of a set being finite is just we have this geometric picture that's incredibly obvious, but actually translating that into some sort of formal language is phenomenally difficult. So I was really sort of wandering around with no idea about what was difficult and what was easy. And of course, also at the back of my mind, I'm like, I'm interested in, I'm interested in the Langlands philosophy, things like that. And there was nobody in the area who seemed interested in the Langlands philosophy, or I hadn't found anybody for a long time. And then it turned out that the Newton Institute has some conference called Big Proof in summer 2017. And I was too late to register for it, but they live streamed all the talks. This is before COVID as well. They were live streaming all the on the Newton Institute, you know, on some bespoke software on the Newton Institute website. And so I watched some of these talks, and this talk by Tom Hales on how he proved the Kepler conjecture using Isabelle. I mean, the story was he announced the proof. He reduced this hard conjecture about sphere packing to a question involving sort of 70,000 nonlinear inequalities that he'd written a computer program to check. And so, some people had raised some philosophical objections with this proof. It's like, you know, if this code is wrong, then the proof falls down. And who's checked your code? And so he rewrote the proof. You know, it took him it took him many years, but he rewrote the proof in a theorem prover. And you know, so clearly had proved the Kepler conjecture. And he won prizes for the work, but he didn't win prizes for the formalization, right? You know, when the formalization was done and it was quite clear that the proof was correct, people had already started giving him prizes, and that was for proving the conjecture, not for the formalization. But he's also, you know, works in, you know, automorphic representation theory, the same area as me. And his talk was a little bit about his Kepler work, but his talk was about, you know, trying to get these systems to actually engage with modern research mathematics, which was not something I really thought too much about. This is a slide from his talk from Cambridge. He suggested that the problem of even teaching computers about research level mathematics was going to be hugely difficult, because even to state the questions that we think we've proved, you know, like local and global class field theory were proved 150 years ago, but to even state the main theorems in their current form would involve a huge amount of work to even make the definitions. You do the first thing on his list is schemes, and the last thing on his list is perfectoid spaces. And a lot of these fancy things were, you know, theories that part of my own research work. And so it occurred to me that actually maybe one could use this software to do, you know, hard research. And that was not, you know, what I'd initially brought into the system. So Hale suggested Lee might be a good theorem prover for doing hard research mathematics. So I started learning about Lee, which was something I'd never heard of before. There was a book, Jeremy and others had written this book, Theorem Proving in Lean, and you kind of think, oh, that sounds good, because it's about proving theorems, but, you know, it doesn't prove the order of the element divides the order of the group. It doesn't, you know, in some sense, there's very little mathematics in it. But the idea was I wanted to integrate this into this introduction to proof course somehow. So I started, you know, I read the book, did all the exercises, and then I started trying to formalize my own problem sheets. And there were 10 problem sheets in this introduction to proof course. So this is the first part of the first question on the first problem sheet, as written by me. If x is a real number, I mean, that looks like a completely reasonable maths question, right? X is a real number. The quadratic has got two roots, right? X equals 1 and x equals 2 are the two roots. I've just taught the students about implication in lecture 1. So the question is, can you prove true or false? You know, x equals 1 or x equals 2 implies x equals 1. So of course the answer is false, right? Because x can be 2. So that's what the students get from me on day 1. And so then I kind of think, great, so let's prove this theorem in Lee, because this is not difficult, right? This is the first part of the first question. And I'm staring at this question thinking, well, what does the question actually mean, right? What is x? Like, is it a variable? Like, is it a fixed real number or a varying? What does this question actually mean? And it took me a while. I mean, like, if x is 1, x is a real number, right? So we don't know anything about it. So let's say it was 1, then it's true, right? Why am I telling the students that this question is false? Because clearly sometimes it's true. In fact, if x is anything other than 2, then this implication is true. If x isn't 1 or 2, then both sides are false, and false implies false. So the question is almost always true. And yet I'm telling the students that it's false. And all of a sudden, I'm realizing, you know, There's me. I've got awards for teaching at Imperial, but I just asked them this completely ill-specified. No wonder the students are struggling, because I don't actually, when it comes down to formally writing down what this question is, I realize that in some sense I don't know myself. I know what x is. X is an arbitrary real number, right? What does that mean? It means it can be 2. It seems to mean that. But somehow it mustn't be all the other numbers that are all of a sudden I was learning things already, right? Learning things about how lousy my own course was. There was another question I went into about counting equivalence relations. How many equivalence relations are there on a set of 2 of them? And I've seen smart students say there's infinitely many. And the reason they're saying this is because I define an equivalence relation, but I never say what it means for 2 equivalence relations on the set to be equal. and there's a subtlety there. So I learned all of these things whilst trying to do my own problem sheets. So anyway, so it turns out that the question means for all real numbers x this is what the question means. True or false, for all x, this thing implies this thing. That's what the question really means. And of course, now I type in the model solution, expecting Lee to say, yes, okay, that's done. And when you type in this thing like this, it says, well, no, you haven't done it. Because now you've got to prove 2 things. Firstly, you've got to prove that 2 satisfies the quadratic. You've got to prove that 2 is not 1. And when the software told me this, I just realised I was in love. Because, in fact, that was exactly... These are actually the correct conclusions. This is exactly what we've done so far, right? We've got to prove that 2 is a root. And we've got to also prove that 2 is not equal to 1. And I do not have the skills to prove that 2 is not equal to 1, because that's not a question that anyone's asked me before. And I want you to ask, let's ask a first-year undergraduate proof that 2 is not equal to 1. What kind of... They can't answer that question. It's just true. Is it an axiom? It can't be an axiom, right? But it must be true. Where's this coming from? And so you look at the definition, so I go on the lean chat and start asking how to prove these questions, and they're just like, well, it depends. It depends on which 2, right? Because there's lots and lots of different 2s in Lean. There's the integer 2, the real number 2, the rational number 2. They're all different objects. So I tell them, as it happens, the question was about the real number 2, because I've just randomly written real numbers when I was writing this, when I was writing the example sheet. And so they're like, oh no, it's a nightmare. Because the real numbers are defined to be equivalence classes of cosine sequences. They're really complicated. A real number is a really complicated object. But they did assure me that it was true, and they remarked that if 2 had been the natural number 2, this would not have been true, right? Because 4 take away 6 is 0 in the natural numbers, because natural number subtraction is a pathological function. And similarly, to prove that 2 is not equal to 1, the tools weren't there in 2017. So I've sort of made this commitment that I'm going to use this theorem prover in my classes, and I've realised I can't do the first question on the first part of the first problem sheet. But fortunately, then some random person comes out of the woodwork and just says, well, if you want a tactic that solves these goals, you can write one. All you have to do is be some expert in writing lean meta programs, and people out there exist. And they don't know which meta programs to write. And here's some random mathematician saying, can you write a meta program to solve basic equalities and inequalities in the real numbers? They're like, yeah, sure, I'll do that. So there was sheet 2 is about square roots. Lean didn't have square. It had the real numbers and had the proof that a non-empty bounded set of real numbers had a least of a bound. So, you can't see what's happening. I can see what's happening.
Sorry about that, Kevin.
Is it?
The people online can still see the slides. I don't know what's going on with us.
Okay. So sheet 2 is square roots.
Can I?
You do it?
No, it doesn't like me either. Yeah. I'll just see if I take it. Yeah. Well, when you talk, everything was going well.
Oh. I went back. And then I went. It just doesn't have the square roots. Oh, there we go. No, yeah. Square root of x.
Does e
explain why it's not true for natural numbers?
Oh, because the definition of subtraction on the natural numbers is that it takes two natural numbers and then it outputs a natural number. The concept of subtraction is it takes two terms of a type and then outputs a term of the same type. This is like adamant that that's the only thing that subtraction can do. So if you give it two natural numbers and then ask it to subtract them, it will return a natural number. So it's like, I've got to return a natural number. Like, it can't be -2 because that's not a natural number, that's an integer. So I'll just return 0. And then when you add 2, you get 2. So, yeah, hard luck.
So the participants on the online mode are now a bit more offended than us.
So it's true for integers. But for integers, you have questions about division. Like, if you have integers, then 1 divided by 2 times 2 wouldn't be 1. Because again, division would take two integers and it would necessarily return an integer.
So they just have like a default that has to return, so you say it returns 0 whenever it's not a natural.
Yeah, I think for division it rounds. I think if you ask 5 divided by 2, it will return 2. If 5 and 2 are integers, it will return 2. But if they're rationals, it will just return 2.5. It's just this is how the type here as well. Oh.
So why is the type checking not checking that the result is possible? Why is that not there?
The subtraction is that computer scientists are perfectly happy with this kind of completely broken definition of subtraction.
Right, so definition you could define correct subtraction, which only subtracts if one is bigger than the other.
Yeah, you could define modified subtraction, which takes two natural numbers and a proof that the first one is at least as big as the second one.
Right. I could give you the proof that the first one is bigger than
Yeah. So now this is a different function, right? This is a function with different.
You evaluate the proof and you'd be entitled to decidability.
Well, I mean, you just have to. It would just be a different function. It would be much harder. It would be really irritating to use because every time you do a subtraction, you'd have to. In fact, the slide I was about to talk about, the square root slide, has the same nonsense in it. So the definition of square root, I defined. You have all these facts about the real numbers on an empty bounded set of real amount. But it didn't have the definition of square root. So I defined the square root of a non-negative number to be take the real numbers whose square is less than this, and then take the sum. And so my input for the square root function, it took a number and the proof that it was positive, and returned its square root. And it's really hard to work with. It was like a disaster because every time you took the square root of 2, you had to prove that 2 was positive. And if you kept mentioning the square root of 2 in the middle of some argument.
Can I suggest that we all log in on Teams?
Yeah.
And then we're going to see the screen until the team prepares. Do we all have the? Do you all have the Teams link?
Was it in the email?
No, it wasn't. Let me just send an email.
That's it.
Yeah, I emailed it from just well, actually, I need to argue that Teams chat is not
So, would you like to sit here?
I'll do what I'm told. I'm quite happy to.
Apologies for this.
I'm quite happy to do what I'm told.
Again, he's sharing here. As I said, when you thought everything was going well. I'm really sorry about this. So I'm just going to send everybody Teams invites.
We need to meet.
Yeah, yes, and we need to meet the staff. Sorry, I've done this by default because.
I was going to ask it. Yes, you can send it to her.
Okay. Okay, so you should have in your emails the pin invite now.
There you are.
I know we have this of course. Okay, you're back.
Shall I go on?
Yeah,
Yeah.
please.
So let me, in the interest of time, let me just, so sheet 2 was about square roots, which were kind of fine. So I was quite weak at the software at this point. I wrote one of the
She was to prove that the square root of 3 was irrational. And I wrote a gigantic proof of this. It took me hours. So clearly, this was supposed to be a simple problem sheet question. But I was really struggling to do it. So this is part of my proof. This ended up on the front page of the LMS newsletter, to my amusement. There's my proof that the square root of 3 is irrational, sort of jazzed up by one of my children. She. I understand. Where's my book? Yes, there's that.
But we are obviously not good at doing turtle stuff anymore, right?
Did you remove it?
No, it should have been there. It copied it. Sorry.
Maybe just talk about the square roots.
I just don't know what to say.
Does my talk not actually go past this page?
Seems the file is empty, but
I've got a computer somewhere. I've got the talk on my computer. Can I just go to my computer? I've lost it back.
I don't know, try to open it in preview. Oh, but you don't unlock on that.
Are you telling me that I gave you a dodgy?
it seems empty.
Sorry.
Web browser? I don't know what to say.
Yeah, I've still got my. Oh, yeah, no, that looks good. Yeah.
Yeah.
We've got that bit. The question is what happens after that. Keep going.
Computer doesn't want to work with me,
Oh, okay.
but yeah. Are we back?
Yeah.
Yeah, the question is what happens after that. What happens in sheet 3?
Is that not the same slide?
Yeah, we've had. No, it's not. Oh, there we go. That looks good.
Yeah, so we're in 2019.
Yeah, great.
Oh, excellent.
So let me start sharing again. That kind of thing now?
Yeah, that's fine. So, just briefly in 2018, what did we do? We did complex numbers. These were in our introduction to proof course, but the problem is, of course, e to the I theta is cos theta plus I sine theta. If you actually think about what that involves from first principles, you're rearranging some absolutely convergent infinite sum. And we'd only just got the definition of the complex numbers. So this is somehow not really an appropriate question. And I had to make a big call here. It's like, I'm teaching this course, am I supposed to like change the syllabus or like change the problem sheets to make them specifically more appropriate for this theorem prover, which here we've got the definition of the reals, we've got the definition of the complexes, but we certainly don't have a theory of functions of one real variable yet. So I can't prove e to the I theta is cos theta. I can't even define cos theta. I can write it as an infinite sum, but now I've got to prove that infinite sums converge. So I realized that I couldn't just slot this thing in, right? So number theory is much easier, and then equivalence relations and functions are much easier. And then there was a last question about f minus e plus v is 2, that just involved some kind of appeal to geometric intuition at some point. And I got really quite confused about whether this was mathematics at all. Anyway, I just did, in 2017, I just did it. I would do some lean online, and I do lean in the lectures, and I started a club, and I said if people were interested, they should come along. And And my idea about what was going to be happening, like my idea was I was going to teach weak students about equivalence relations, but all that happened was like the top students came along because they could hang out with a lecturer. Yeah, the people that knew the course already came along because they were interested in, this was like the course again, but in hard mode, basically. So that wasn't the plan at all, but was not unexpected given what happened. So I would show the students Lean, and we would run into interesting problems, and I would blog about them, and then students would work on them on Thursdays. So one of the things that came up at that stage was how to build an naturalness from scratch. So that was what happened. And summer 2018, I just did a bunch of informal Lean projects that found their way into the maths library, many of them, and students were interested for funny reasons. Students were interested because they were doing something new. I think they felt like they were contributing to research. So I didn't really know what I was doing, but we hired Athena, who came along and prodded the students and interviewed them. I could use the software by this stage, so in 2018 I did basically the same thing again, and Athena tried to work out what I was doing, and you could read her paper with power to see the conclusions, but somehow the main conclusion that they told me was that what I was doing was completely stupid. Basically, you can't. My naive idea about teaching a weak student how to use Lean by saying, look, here's a complicated piece of software. It does equivalence relations really well. Now go ahead and do equivalence relations in this software. This is just never going to fly, especially if it's not going to be compulsory. So that's the old course. And then there was a curriculum. I'll skip some things because these are time constraints. And then there was a curriculum review at Imperial, and I put myself onto the curriculum review team and rewrote the Introduction to Proof course in 2019. So I'll just talk about the slides I'm going to skip. So I rewrote the course, and so it didn't have things like e to the I theta is cos theta plus I sine theta in it anymore. Stuff that was really causing me problems. And it had more stuff about surjective functions, which was really easy to do in the theory. So we did sets, functions, and equivalence relations, basically. And this new syllabus came along in 2019, and I was now teaching a course which was much more aligned to the stuff that Lean found easy. So you could do Lean in most lectures. But it was still completely optional, and it was still the case that most students were not remotely interested in it, for the reasons that had been flagged to me by the education specialists. But if a student is struggling, then clearly they're not going to decide to also start learning how to use a complicated theorem prover. So that's my experience basically with first year undergraduate teaching. But more recently, in 2020, so this is, so let me skip then to spring 2021, where I tried to do something completely different. I taught a course of PhD students, based on what Athena had told me. I taught a course of PhD students. So the point is, you can't teach them the maths and how to use a theorem prover at the same time. So, okay, let's start with a bunch of people that know the maths already. So these are PhD students, typically in pure mathematics. And I taught them the same material, right? In the first of the workshop, we did sets, functions, and equivalence relations again. But this time to PhD students. And it was all, COVID had happened, so we ran it all on Discord, and there were 15 or so students, and they all came week after week. And we would just meet on, Discord is like a chat, a chat server. We would all meet in a voice channel, and they would all share their screens. And I'd taken sabbaticals to write this course. And so I spent all week, every week, sort of trying to figure out how to teach a certain area. So like, for example, the first workshop, the sets, functions, and equivalence relations, it was a complete disaster. Because I thought that, well, all these students know sets, functions, and equivalence relations, so I'm lost. I'm just completely, I don't know how to, I can't see the bottom of my screen, I don't know how to use Windows.
No,
Apologies.
No worries.
Like, yeah, but you see, you can't see what's happening at the bottom.
because there is the window.
This one.
Just, oh, that's nice.
Yeah.
But, yeah, okay. Well, thank you. Yeah, let's work with that. So again, I was still giving them far too much to do, but by the end of it, we got to some interesting mathematics. And as I say, this was optional, but it was working great. And I was teaching PhD students. You know, at the end of it, I've got a PhD student formalising the statement of the Burton-Swinnerton diagonal. And this is, again, something that's never been done before in any theorem proof. And so I'm teaching the undergraduate course again, kind of on autopilot now. I'm not really pushing it because the first year undergraduates, I don't quite know what to do with them. You know, they come along and they say, oh, great, I want to do linear maps. It's like, yeah, we've got linear maps now. But the last thing I wanted to talk about was I've been teaching a course for third year undergrad. I went through some process of getting a course approved by the teaching committee, and I'm now teaching an optional course for third years. And that's just run for the first time. So this is the last part of my story. So this is the third year course. This is the first course I taught where lean is compulsory. You know, you have to write 3 projects, and then you get. Paola is always telling me that orals are important, so I examined all the projects. I read the project and then I gave an oral exam. So, and that was the titles, you know, this was given to them on day 1. These are the 3 projects they had to do. Formalise, some of you learned in first year, some of you learned in second year, and some of you. So it's completely. I had COVID last week, but I'm no longer infectious and I'm testing negative. Okay, so that's what I'm talking about. So that was the story, and I didn't know what I was going to get, and I just got completely random things. I was looking for. Yeah, that was basically what I told them I was after. And it worked. I got some very weak students. I also got some students, because I've been banging on about lean at Imperial for 4 years now. There's some people who are like 4th year undergraduates who've been doing lean for 3 years straight. So there are some people in the course that are better than me at lean. And there's some who've never seen anything like it before. And you know, there's some people who it's the only pure module they're doing, and they're doing a bunch of stats modules, or whatever. So it's really interesting course to teach. I was planning on doing the same material I taught to the PhD students, like let's do filters, let's do uniform spaces, you know, let's do exotic stuff. But I found that because of the nature of the course, I told the students that they were supposed to be formalising stuff from their other courses, and they didn't want to hear stuff that they hadn't learned about in other courses. Yeah, they wanted to, you know, the third year graph theory course looked perfect. So they wanted to see how to do graph theory in lean. This was something I knew nothing about. I've never used graph theory in lean. I don't care about graph theory. I care about algebraic number theory. So I was kind of frantically, you know, I was completely derailed. I was frantically trying to learn how graph theory works in lean. But I did, you know, because it was what they wanted. So there's 22 undergraduates, 19 straight, 2 doing a joint maths and computing degree, and 1 straight computing. The notes are online. I'm quite proud about them, really. Do you think this will work? There we go. So there's what the course looks like, and I don't. Were they useful, these notes, or did you never look at them?
Yeah.
I think
Yes.
that they're not showing on. Oh, okay.
I wasn't really sure. Oh. So the final project deadline was last Friday, and you could talk to the students about what they thought. But basically, I think that everyone who went to the course is actually capable of writing lean code at sort of undergraduate level. So that was kind of the point, really. So here's the summary then. The idea was to teach weak students about equivalence relations. I can't work out how to do it. So now I'm teaching random third year undergraduates how to formalise mathematics that they already know or think they already know. And more than once, I think Beth was one of the people that said this. She felt like she was a first year again, and I felt just the same when I was trying to work out how to do this stuff. And I don't know if that's a good thing or a bad thing. But that's the end of my talk anyway, so sorry for overrunning.
Kevin, and sorry for the technical difficulties. So, do you want
Okay, I'll come up. Shall I go on up till noon then? Okay.
And I'm going to be around all day, so it's not